Welcome. I want, on behalf of MysTech, to welcome all of you to this season's MysTech webinars. Tonight is our first. Just as an aside, tomorrow night begins the Leonid meteor showers that will peak on Tuesday and Wednesday nights. So I'm glad we're doing this tonight ahead of those. After this first webinar, we will take a break for Thanksgiving and Christmas, and then resume on Sundays in January, starting on the 9th in 2022. To kick off this season's MysTech webinars, we are most fortunate to have with us today Professor Valdemar Setzer, who is coming to us from Sao Paulo, Brazil, where spring has been in full bloom and summertime is just beginning. He is a so-called retired professor of computer science at the Institute of Mathematics and Statistics at the University of Sao Paulo. Despite being retired, he has remained involved with the university, supervising theses, conducting research, and teaching classes. Hey, Valdemar, that does not sound like a real retirement. Come on. Valdemar was founder and director of the Electronic Computing Center, head of the departments of Applied Mathematics and Computer Science, and president of the undergrad committee, and active in his profession in numerous ways, including a member of the Academy of Sciences. He has been a visiting professor at several universities, including in Austin, Texas, the University of Texas there. He has been a long-term member of the Anthroposophical Society, joining it in 1971. And he has been an invited speaker for events at the Goetheanum or sponsored by the Goetheanum. He has 12, or is it 13 now, books published with numerous technical articles as well. We are delighted to have you, Valdemar, with us here tonight. Professor Setzer will deliver his second webinar on January 9th. You're all invited to that as well. That will be followed, as I mentioned, by 5 more MysTech webinars on the successive Sunday evenings. We hope you can join us for these webinars that are so important for these times in which we live. I ask you if you could hold your questions until the end of Valdemar's presentation, and we will stay on to try to answer all of your questions. So now, please join me in welcoming Professor Valdemar Setzer to this, the first of this season's MysTech webinar series. Valdemar, over to you.
Okay, well, good morning, good afternoon, good evening, depending on where you are. Here in Brazil, it's already 9:35, in the evening. So I hope we are going to have a nice evening here, or a nice day, or a nice afternoon with my talk. I have to excuse myself because of my English. Unfortunately, I don't have opportunities of speaking English. And secondly, at my age, one begins to lose all the foreign languages that one knows, So I hope you'll be able to understand me, and I'll be able to express myself with some fluency. And I have to thank a lot for the invitation. I have to thank Andrew especially for the invitation. This is a very special talk because it involves some technical subjects and also philosophical ones from the anthroposophical point of view. So let's go on. And you see, at my age, one forgets lots of things. the first thing I forgot for this lecture is to prepare an assessment form with three main questions. What were the most important things I have learned? What were the biggest doubts that remained? And comments. This is an assessment that I was passing after each lecture at the university. And I recommend people that teach and give lectures to try to make such an assessment. It was inspired in what is still called a 1-minute paper. I think it was developed, the idea was developed in the University of Berkeley, or the University of California at Berkeley. But there are many different versions. This is my version. So I forgot to prepare this form, but I'll do that tomorrow. Tonight it will be too late after the lecture, but I'll prepare it tomorrow and I'll pass the link to Andrew. And Andrew said that he has the email address of everybody that is participating. So he'll send you the assessment form, and please answer it or fill it up, because I'm going to copy all of the assessments into my website, into a special page that I'll also send the address, and I'll comment on what deserves to be commented, right, or answered. And it will be very interesting for you to see what other people wrote in that form, right? And my comments for them. So, and if you enter my homepage, you'll see lots of assessments for each lecture that I've been giving remotely online. I have assessments, but they are all in Portuguese. But let me tell you something. If you enter my website, my homepage, and you'll see some papers or interviews and so on. There are many in English, but not all of them have been translated into English. If you take some of them in Portuguese and you use the Google Translator or the one from Lingui, right? They are making very good translations to and from English. If you translate from another language to a third language, then the translation is not very good. But from English and to English, the translation is fairly good. I've been making translations from my stuff into English, and I've been using a Google Translator, and I have to make very small corrections, grammatical corrections or semantical corrections. So let's go on. And I would like you to take a piece of paper and write on it, is the human, yes or no for the following question, is the human being a machine in the sense of being a purely physical being? This is not a fair question for anthroposophists because I can guess, very well what you are going to answer. But figure out there would be some people that have no acquaintance with anthroposophy. I used to make a statistics on that question, and I always got half and half. About half and half. Half people have written in a piece of paper, and they, in how to say, personal lectures. How do you say that? Presence lectures. I get those piece of papers, and then I count them, and in general it's 50-50. For yes and no. Okay, I presume anthroposophists will certainly write yes, okay? And I'll see why, we'll see why. So this is the summary. We have a long way to go, so I have to be a little bit fast on my presentation, okay? So in 1694, Leibniz built a mechanical calculator with new features that didn't exist for mechanical calculators. And he wanted to do something that was quite a bit researched last century. He wanted to build a machine that could manipulate symbols, right? And prove if a sentence of logical was true or false. And that was quite advanced for his time. So, and in 1928, David Hilbert, one does not say David Hilbert, but David Hilbert, he was a German. He proposed a conjecture which is called the Entscheidungsproblem, the problem of decision, the decision problem. There are other ways of, in fact, he didn't formulate in this way, but one can understand his formulation as I have put here. Has every well-formed mathematical problem a solution? You know, that's a very interesting question. For instance, for those that know what a second degree equation is, or remember that, you know, if one asks this question, does a second degree equation always have a solution? Some people say no, because there is the square root, you know, for the roots for the second degree equation. And if the square root has I don't know how to say that, has an argument that is negative, then there is no square root. But in fact, it has in what one calls the complex plane. And here is an example of such an equation. And one gets the square root of -4. -4 squared gives 4, which appears here on the other side. So x is plus or minus 2 times the square root of -1, which is called the complex constant I. So it has a solution. So one could think, does every well-formulated mathematical problem a solution? And this was the Entscheidungsproblem, the decision problem by Hilbert, right? And what happened is that in 1936, this nice guy, Alan Turing, I don't know how to spell it exactly in English, Alan Turing showed that the Hilbert's conjecture was wrong. There are mathematical problems, well-formulated mathematical problems that for which one cannot tell if they have a solution or not. And these are the so-called undecidable problems. So there is a whole field of mathematics which is called decidability, you know, which points to problems that have a solution or don't have a solution, or one doesn't know if they have a solution or not. There are many of such problems. We are going to see one of them, which was introduced by Alan Turing. Okay, so to answer this question, the Entscheidungsproblem, Turing had an idea of what I have described as a genius idea for his time. He invented a machine, but this machine could not be built. It's a formal mathematical machine, abstract machine, right? And he devised such a machine to answer this question. So at 1936, he was already thinking in terms of machines manipulating symbols and so on, which was, you know, quite advanced for his time. It is possible to build Turing machines with some restrictions. We are going to see which ones, but they would be very, very inefficient if we would build such machines, and we'll see why. Okay. Now, I have to call your attention to the fact that this machine, the Turing machine, has nothing to do with the machine in the movie The Imitation Game, which some people have scene, right? The imitation game deals with a machine that Turing developed to decode a machine that was developed by the Nazis, the German, during the Second World War, to code their messages. And Turing was involved in this team that, or he directed a team that broke this machine, which was called the Enigma machine, right? It has nothing to do with we are going to see as a Turing machine, but this is much earlier, 1936, right? So let's see what is such a machine. And later on, you are going to understand why I introduced the Turing machine into this lecture. Well, it's a mathematical abstract machine, as I have described. It is also called a formal automaton with the following configuration. There is a tape divided into cells, right? And into this tape, one can have a symbol, one symbol per cell, right? Here I have written some of these symbols. The B's state for blank, so the rest is blank, right? And we have here a hash. I'm going to call these number symbol as a hash. I have seen in the internet that this is one of the names that is given to this symbol, right? And this sequence of symbols begin with a hash and then has ones and zeros and ends with a hash. And this machine, these, by the way, these tape here has infinite number of cells, okay? This is the main reason why it's abstract, you know. Physically, there is nothing infinite, right? I have a book written on the infinite in Portuguese, unfortunately. I have also given lectures on that, just to show, you know, what mathematical infinite is, and it cannot be physically implemented, right? Okay, so it has a tape, infinite tape, and a read-write ahead. I'm going to use the name read, but it's absolutely wrong. You know, the first computer language, so-called high-level computer language, which was Fortran, formula translation, in 1954 to 58 by Bacchus at IBM. He had a statement, read, right? This is wrong. A machine doesn't read. Animals don't read. Only humans read. This should be called a recognizable command or something like that. But I'm going to use the common name read and write, right? So this head here has the possibility of recognizing a symbol and changing the symbol, write over some symbol, another one, right? So this is the read and write head. And this head is moved one cell to the left or one cell to the right at the control of this so-called finite control. What is the finite control? It has a finite number of discrete states and controls the read-write head. We are going to see what kind of states are those, right? So let's see the characteristics of the finite control. It has a finite number of states, right? I have written here some of states, you know, with some names for them, but it has to be a finite number. So I have gone up to S sub n, right? And it happens that the machine, the finite control, is in only one state at each instant, right? There is no time assigned to the machine, but let's call it, you know, an instant. At every instant, the machine has to be in only one state. In this case, at T1, instant 1, it's in the state S sub 2. Now it may change to S sub 3. So it has changed to S3 in the next instant, T2, right? We had T1 here, and now we have T2, right? I know that my pointer is very small at your screen, but I hope you can distinguish it, right? So another characteristic is that it can, there are transitions registered into the finite control, specifying from which state to what state a transition can be made. In this case, it shows that being in state S3, it may change to state S1. So in the instant T1, in the next instant T2, it has changed to state S2. So from state S3, it may change to state S1 because the finite control has in itself a description of this transition. Now we're going to see how these transitions are taken. Oh, I'm sorry. There could be a transition to the same state. And some of you will say, well, how do you say, an idiocy, right? Or, what a stupidity, what? Crazy. What a crazy thing. My wife has just helped me. Sonia has helped me. She's here at my side. What a crazy thing, making a transition to the same state. So we are in time, in instant T1, in the next state, instant T2, we are still on state S3. But we are going to see that this is very, very useful, that one can make a transition from one state to itself, right? That doesn't change the state. In fact, the transition is made, but it doesn't change the state. Okay, now how is each transition chosen, right? Or chosen, I'm sorry, choose what? Chosen. Okay, well, in each transition, one specifies a read symbol. So if the symbol, we are in a state S sub I, and there is a possibility of changing to states S sub J or S sub K. And, here one specifies what kind of symbol the read-write head is going to read or recognize. If it recognizes a hash, it changes to state S sub J. If it recognizes a 1, which is the case, one see here, which is exactly the case, it changes to state SK, right? So this is the condition for choosing what transition is going to be taken from a certain state, right? So there is another thing. A symbol is going to be written, right, on top of the previous symbol. In this case, if a hash was recognized, a hash is written over the hash. You are going to say, what a stupidity, writing exactly the same symbol that was there. But this is the way that the machine works, because this way it is the simplest machine as possible. It always changes, but it could change to the same symbol. But if it's a 1, which is recognized here, it changes to an X. So what's going to happen the next instant is the 1 is changed to an X. So you see here is a 1, and this 1 is changed to an X when the transition is taken. But there is another condition for the transition. It's the head should be moved, in this case, to the right. So it was here. The 1 was changed to X, and the read-write head was changed to the right, 1 cell to the right. So this completes the transition. The first symbol in the transition is for choosing what transition is going to be taken. The second one, the symbol that is going to replace the previous one, and then the transition, the head movement. In this case, to the right. In that case, if the transition to SJ would be taken, it would make a transition to the left. In this case, they made a transition to the right. Okay, good. And after all that, the transition is taken. It wasn't in the state SI, and it goes to the state SK, right? So here it goes to the state SK. Now the finite control is in the state SK. Remember that there are a finite number of states. The tape is infinite. In each cell, one has a symbol. In fact, I should say that this is a special Turing machine that I presented you, because I thought this would be the simplest one. But a Turing machine could have, for instance, just the symbols 0 and 1, no other symbol, or instead of 0, blanks and ones. And it would still be able to calculate everything that this machine that I am presenting you does. You know, we are going to see a little bit in detail about the power Turing machines have. But this one, if one would have just blanks and ones on the tape, oh no, I'm advancing what I'm going to show you next. So each transition could be described in text-wise with 5 symbols, which is called mathematical a 5-tuple, 5 symbols, an ordered sequence of 5 symbols. The first symbol describes the present state, the actual state, the present state. The second symbol, the symbol that has to be recognized under the head. And the third symbol, the symbol that is going to replace the symbol that was under the head. The fourth symbol, the head movement, and then to which state the transition should be made. In our case, we had this transition that was taken, right? SI, the symbol under the head was 1. It was replaced, would be replaced by an X. The head would be moved to the right. I'm sorry, I forgot the symbol in Portuguese. This is 24. I have to change that. I'm sorry. This should be left here, L, and here should be right. Unfortunately, I didn't change the symbols in the original presentation in Portuguese, esquerda e direita, E and D, but in fact should be left and right. I'm sorry. I hope it will be the only mistake. Well, so the 5-tuple then, it has, as I described, these 5 symbols. I wrote here what they mean. Present state, the symbol to be recognized, the symbol to be written, the head movement, and the next state. Here should be right, an R instead of D. Okay, so again, here, I forgot to change all of them. Well, okay, and it's important that there is an initial state, you know, from heavens, you know, comes the fact that the machine has to start on this state. It could start in any state. One has to specify in which state, only one state, the machine will start its functioning, right? And there is a set of final states. For instance, these 2 could be final states, right? Okay, mathematically, one could describe, this is not important. I'm just writing down, you know, for the sake of formality. The whole machine could be described also of a 5-tuple, a set of the final states. You know, here would be, S would be the set of the name for the set of all states. This is in the initial state, the set of final states. This is the tape alphabet. An alphabet formally is a finite set of symbols, any kind of symbols. If they form a finite set, a finite number of symbols, then it can be called an alphabet. Any collection of symbols. And this is the transition function. This is very important. This describes the transitions that we have seen. It takes one state, one symbol under the head, and it goes to another, changes the symbol under the head, makes a head movement, and it makes the transition to another state. But all this is just formality. It's not very important. M is a set of the left and right movements, so symbol for left and right movements. And what is the processing of a Turing machine? It starts with the head in a certain tape cell. No, one has to specify it starts here at the tape, in some cell at the tape, and the control in the initial state. And then the transitions are followed, are taken, right, as I have shown you, until the machine reaches a final state, or in the present state where it is, there is no transition defined for the input symbol. There is an input symbol there, for instance, Y, and there is no transition with symbol Y, right? So this machine has to stop. One says that it has stopped or halted. Halted, we are going to see why this name, halting, right? Okay, so here I have described what I told you. As a matter of fact, for those that have reached us a little bit later, this presentation is on my website. I have written it into the chat. Later on, we are going to maybe Andrew could copy it again, because in Zoom sessions, people that get later into the session don't see what was written into the chat before, Andrew. Okay, so now I'm going to give you an example of a Turing machine after all these theory, right? So suppose we have the problem of checking the parity of a binary number. What does it mean? Verifying if the binary number is odd or is even. And this is very simple for binary numbers. If it ends with a 0, it's even. If it ends with a 1, it is odd. That's because when one has a binary number, the rightmost digit has to be multiplied by 2 to the power 0, which is 1. The second one to the left, 2 to the power 1, 2 to the power 4, 2 to the power 3. So this has to multiply by 1, has to be multiplied by 1. The next one to the left by 2, the third one by 4, and the fifth one by 8 powers of 2. So this one represents, in fact, number 10, decimal 10. 8 plus 2 is 10, and it's an even number. Here one has 9 represented binary, so it's an odd number. So even numbers have end with a 0 before the hash, the rightmost hash, and this one ends with a 1, which is then means that it is an odd. So the machine should transform the tape into the following. It should leave the binary number 1010, right, and then write even, and then the hash, or it should write odd and then the hash. So let's see how would be a Turing machine to do that. Well, yes, let me describe you how this machine is going to work. We begin here at the leftmost hash, and then one recognizes a hash, writes a hash there so that we don't modify the leftmost hash, and then it goes to the right. Right? The head goes to the right. If it's a 1 or a 0, goes to the right. If a 1 or a 0 goes to the right. So it jumps over all 1s and 0s until it gets to a hash. When it gets to a hash, it moves the head to the left and verify if it's a 0 there, or it's a 1. So there will be two transitions, one with 0, another with 1. If it's a 0, then it moves to the right, writes an E instead on the place of the hash, of the rightmost hash. Then it writes a V in place of the blank, and then an E, and then an N, and then a hash, and then we'll have that. And correspondingly, if the tape has a not binary number, it will write ODD hash at the end, right? So let's see and I have described the algorithm here. You can read it when you download my presentation. Okay, and here I have presented a state diagram for the machine. As I told you, there is an initial state, so this arrow here says that this state will be the initial one. And what it does, recognizes a hash. And if it recognizes a hash, which is the case here, it replaces by a hash and then goes to the right. So the head now is pointing to the 1 at the tape, right? And here one see how useful are loop transitions to the same state. So if it's a 1, one jumps to the same state, but the head moves to the right. If it's a 0, one jumps to the same state. And, I forgot to write down here. I'm sorry, I am in 32. Okay, there should be 0, 0 left. I'm sorry. Here should be 0, 0 left here. And if it reaches so what this state is doing is jumping over all 1s and 0s until it meets a hash. When it gets to the hash cell, it replaces by a hash and goes to the left. So the head is now pointed to in this case to the 1. If it's a 1, leaves the 1 there and goes to the right. So now it's pointed to the hash again, but now replaces the hash by an O, moves to the right, replaces the blank, which will be here, to a D, goes to the right, and then I'm sorry, this B should be a small b. I'm sorry, I have revised this twice, and I still have some problems there. So it should be a small b. It replaces it by the D, which is this, the last D, goes to the right, and the blank is then replaced by a hash, which is this last hash here, and goes to the right. The head stays there at the end, the first blank after the solution of the problem. So this is I hope it's, I made everything understood. It's very, very simple, you understand? Now, suppose here at the beginning, the leftmost digit would be a 0. In this case, this sequence of self-transitions would be taken, which would replace first the hash by an E, and then the blank by a V, then the blank by an E and N, and then always going to the right, and then again the last transition. You see that I have optimized this state diagram, because from this state here, for when it would have met an odd number, binary number, it could jump to another state, and from that state to another final state. But here I took advantage that we had already for the even, right? We had already, or for the odd, we had already this last transition, and I have jumped to this state, right? So we have only one final state. We could have any number of final states. So I hope this is understood. It's very, very simple. If you don't get exactly how it works, if you download my presentation, you'll certainly be able to understand what I mean. And here I have the same state diagram with comments. You see, this state diagram is a kind of programming language. And if program in any programming language should have lots of comments, otherwise one cannot understand what the program does. So good programs are full of comments specifying what each comment or each group of comments or instructions do. And I have done exactly this here, right? For instance, this one, I commented, go to the neck to the first digit. So it was, the head was here under the hash, it goes to the right to the first digit. And here I wrote jump over zeros and ones, right? And here is correct, 00R, which was missing here, right? Here, it was missing here, I'm sorry, but here it's correct. And so on, I have commented each group of each transition or group of transitions when any comment would be useful, right? So if you don't understand what this state diagram does, go to the next slide and you'll see the comments and probably you understand, because it's very, very simple. So, and as a good professor, instructor, I have to give you exercises. So Andrew, next week, please collect exercises, okay? So the first exercise is to multiply a binary number by 2. This is also very, very simple. How is this? What is the solution for such a problem? If we have a binary number, to multiply it by 2, just insert a 0 at its after its rightmost digit. So you see, this one is 9, and this one is 18 in decimal. So it has been multiplied by 2, just this 0 here. So you see, it's just a very slight modification of this state diagram. Instead of writing even or odd, right? It should insert here at the right, instead of the hash, a 0, and then the hash in the next cell to the right, right? So this is very simple, just to train if you have understood how a Turing machine works, right? And here we have a complex example, which I'm going to describe because this will be very, very useful later on. The problem is the Turing machine should be programmed so that it would add 2 binary numbers, 2 unary numbers. I'm sorry. I don't know if you are acquainted with the unary number system. The unary number system is what I call the cigarette match system, right? We could have matches instead of one, just matches, right? So if we have 3 matches, it's the number 3. If we have 5 matches, we have number 5. So when we want to add number 3 and number 5, this is the simplest numbering system that exists. Turing machine could be programmed to use only the unary system, and it could do everything that a Turing machine, as I presented you, does, with other symbols. Okay, so how would one solve this problem? How would one program a Turing machine to solve this problem? And it would be very interesting to ask you this question, right? Yes. And some people say, well, just look at if there is a 1 here, put a 1 at the end. If the second one is a 1, put another 1 at the next cell after the first one. But how is it, could it be done? You know, if you move the head up to the rightmost hash and writes here a 1, how do you know which one was transposed, you know, with your program, transposed here? In fact, it was not transposed at all. You just replace the hash by a 1. So the solution is the following. It's a trick, you know, very common trick that one can use in programming Turing machines. You come here to the leftmost, you are on the head under the hash. Go to the right, and if it's a 1, replace it by another symbol like an X, right? Replace this one by an X, and then jump over all ones, plus symbols and equal symbols until you get to the hash. When you get to the hash, when the machine gets to the hash, write a 1 here. Then move to the right and write the hash after the 1. Then move to the left, jumping over all ones. There would be a 1 here, over all ones, all equal and plus, until you get to an X, which was X, X that was written here, right? X or X? I don't remember now. An X, right? Which was written here. Now replace the X by a 1 to preserve the input data right here, and move to the right. If it's a 1, move to the, jumping all over all symbols until you get to the hash, replace it by 1, replace the next blank by hash, move over all symbols until you get to the X. It's an X. X is it's German, I'm sorry. X, it's an X, right? I'm sorry. Okay, and so on. And you get to the plus, you just jump over the plus. Oh, no, I'm sorry, you have to write the plus here after the ones that are to the right, right? And so on and so forth. So what is the machine doing? Is the machine adding? No, the machine is not doing an addition. The machine is recognizing symbols and changing symbols at the tape. You understand? If this is very, very important as a concept. The Turing machine doesn't add. The only thing that it does, it makes the transitions, modifying, changing symbols on the tape. Only that. That's the only thing the machine does. You could also say, oh, the machine is copying these first parts, how to say, first some argument here is copying. No, the Turing machine doesn't copy anything. You understand? It doesn't have a copy instruction. We just have these transitions that I described you. But with them, one may perform an addition. Here, it's a unary, an addition in the unary numbering system. It could use any numbering system and do any solve any addition or multiplication and so on, but it would not be adding, it would not be multiplying or using instructions to add or multiply, right? The result is the addition or the multiplication, right? So this is the exercise that I propose to you. And this is a little bit more difficult. Check if a sequence of A's and B's, there are the same number of A's as B's. So here we have the same number of A's and B's, so the machine should write yes to the right, or here the number is the same, so it should write no. And this is as a fourth exercise. It's a very interesting exercise. Repeat any of the previous exercises without the delimiters, the hash delimiters. right? So the head may start anywhere, right? And if it would be a, how to say, a real presentation, a real lecture, I would ask the audience, how would you solve that? And some people say, well, just suppose the head is here to the left, you just go to the right, you just move to the right until you find a 1 or a plus if the first argument is null, right? But what would happen if the head starts here to the right, right? How would the machine know, know in quotes, right? If it would have to move to the right or to the left to find the number. So the solution for this, I'll give you the solution. The solution is that the head could start anywhere. If it starts in the middle of the input string, then it has to go to the left until it gets to the blank, and then to the right to the first digit, right? Now, if it begins here, it begins anywhere, here to the left of the input data or to the right, it should be do the following. Move, see if it's a blank. If it's a blank, move once, replace the blank by an X, right? Any symbol, an X, right? And then move one cell to the right and see if it's a 1. If it's not a 1, replace it by an X. Move to the left, jumping all over all the X's until it gets to a blank. Replace it by an X and now move to the right. So what the machine would be doing, it would be jumping, one cell to the right, one cell to the left, one cell to the right, one cell to the left, sequentially until it gets the 1 here or to an equal sign if it comes from the right, right? So please try to program this machine. It would not be so simple as the other ones, but, and here we have another thing. You see, suppose you have solved already the exercise number 2. In that case, you had already a Turing machine for number 2. So what you could do is having a Turing machine just to find the number or the input data, right? And then after having found these where the input is, it jumps to or goes to the left, or goes to the first digit to the left, and then it jumps to the previous Turing machine and continues with the same tape, right? We are going to see that later on. So what does the characteristics of Turing machines? So the first thing is that Turing machine does not calculate. The result could be a calculation, but the machine is not calculating. The machine is just replacing or recognizing and replacing symbols. You understand that? This is very, very important as a concept. So the only thing it does is logically choosing a transition based on the input symbol, and in it, change a tape symbol, move the head and change to another state. Just that. It does not calculate. The result could be a calculation because we have programmed it to perform a calculation, but the machine itself is not calculating, right? And so the machine, it doesn't even copy. The machine doesn't even copy symbols, right? It just makes transitions, right? Replacing symbols in the tape or on the tape. And what is the memory? Memory of a computer or a Turing machine is a wrong name. In the origin of computers, it was called storage unit, which is much, much better. Memory is an anthropomorphic expression, which is absolutely wrong. Why? That's why I wrote it in quotes, right? Why? Because we don't know how our memory works. For instance, there is no knowledge where in our memory, the representation for number 2 is stored. It is not known how our memory works, right? It is known how the synapses work, but it is not known what does it mean, the functioning of a synapse, which is connecting, different neurons, right? So the memory of a Turing machine is, or the storage unit of a Turing machine is represented by what's recorded on the tape and the state in which it is, right? Which was the case. Remember when we were the machine was choosing if the number was even, or the binary number was even or odd. If we were in the sequence of states corresponding to even, we would know. The machine doesn't know anything, as a computer doesn't know absolutely anything. We would know that in that state, an even number was recognized if we are in the middle of those, the sequence of transitions, right? So a certain state could represent what happened before, right? Which is a kind of memory also. So the Turing machine is a discrete or digital machine, right? Because it has a finite, therefore countable number of states. It has an infinite state divided into discrete cells, any number of discrete cells where the symbols are recorded, and only a finite set of symbols can be used on the tape. So you see, the tape is the only infinite thing. All the rest are finite things, or finite symbols or transitions and so on, and states and so on. Essentially, a Turing machine simply manipulates discrete symbols mathematically. It's a mathematical machine because it can be described mathematically, right? As I have shown you. And what is the difference between Turing machines and computers? Now, it's very important to understand that any internal processing of a computer can be simulated by a Turing machine. Every internal processing, what do I mean by internal processing? One does not use external units like input-output units, a screen, a printer, a drive, let's say, I forgot my name for it. Sorry for being so old. Well, anyhow, any storage device, right, which is external. So if one consider only the internal processing of computers, one could program a Turing machine to simulate any computer whatsoever, right? So computers are restricted Turing machines. Why? Because they have a limited storage capacity. For instance, my computer here has 8 gigabyte of main storage unit plus a 256 gigabyte of SSD storage, right? So all of this is finite. You can add any pen drives, that was the name, any pen drives you wish, or hard or DVDs and so on. All of them are finite. So computers have always use a finite storage system, right? A finite number of storage units or storage units and so on. But Turing machines have infinite tape. It doesn't have any limitation whatsoever, which is very important for certain kind of problems to solve, right? Oh, I wrote here pen drives. I should have read it. Pen drives, CDs, HDs, and so on. All of them have a limited number of storage. They have a limited storage capacity, but that's not the case of Turing machines. So this is a big difference between Turing machines and computers, right? Okay. And from the von Neumann machine, so-called von Neumann machine, von Neumann was a famous mathematician who worked at the Princeton Institute of Advanced Studies. He was there along with Einstein, and also Turing worked there, right? And in 1945, he had a brilliant idea, a brilliant proposal for the first computer that was built with tubes, electronic tubes. He proposed that data in a storage unit would be represented in the same way, in the same storage unit as instructions, as in the Turing machines, the transitions, right? They would be, in the Turing machines, we had a control unit with the transitions and a tape which could be used for the storage unit, right? But he proposed that they would be in the same unit, and this made a tremendous evolution in computer construction, right? Well, this would correspond to the Turing machine tape, and the instructions of the transitions would also be written on the tape, and the control unit would have a program to interpret those instructions from the tape and use the input data and produce some output, right? Okay. So the computers are also discrete machines that manipulate symbols. This is very, very important to know. This is what I call the fundamental essence of any computer. For the anthroposophists that are acquainted with the philosophy of freedom, Steiner's philosophy of freedom, know that everything has an essence, right? Which is the concept behind the thing. And our thinking completes the perception, having access to the essence, to the concept. So what is the concept, the essence of each computer? I think the fundamental essence is that they are discrete machines that manipulate symbols. So now you are going to learn something very important. Computers don't add. They don't add. They just combine the symbols to give the result that we wish for some addition, right? But if there is an instruction, they have an instruction, add, for instance, 2 8-bit numbers, right? But what they do is that they manipulate, they combine the symbols so that one gets the correct results for the addition. But it's not adding, it's just combining the symbols, you understand? So computers don't add, don't multiply, and so on. They just combine the symbols, manipulate the symbols so that we get the correct answer for the instruction or for the calculation. Okay, so and this is clear from the unary sum exercise. That's why I presented you with that exercise, right? So this is very interesting. Once I gave a lecture, presential lecture, a presence lecture, for some audience that was there before the pandemic. And a dear friend of ours, Rogério Yokuishi Santos, that's his name. He's from Japanese ascendance, Brazilian Santos, and probably the mother was or is Japanese, and he gave this very interesting idea. The Turing machine is the archetype of all digital machines. A very, very interesting characterization for the Turing machine. The Turing machine is the archetype. So if one understands how a Turing machine works, one should understand what is the archetype of all computers, right? So computers have what is called technically macro instructions, which are algorithms implemented in electronic circuits to perform frequent functions much faster, you know, that a Turing machine would do. A Turing machine would be extremely slow or extremely inefficient, right? For instance, there are instructions for doing additions, right? Which are macro instructions implemented through electronic circuits, which manipulate symbols. That's what the electronic symbol circuits do. And the symbols are represented electronically, right? For instance, in bistable, bistable, I know how to say that, bistable circuits, which could be in two different states, right? In one state, it would represent a 0, in another state would represent a 1, right? That's how computers work, right? But a number of these circuits could be put together and perform a sum, an addition, and very different kinds of additions. The addition of 8-bit numbers, 16-bit numbers, 32-bit numbers, 64-bit numbers, and so on, right? Different. So this is the same as in terms of Turing machines. If a Turing machine's T sub 1 would activate, would technically call another anthropomorphic expression, which is wrong. It activates, but it's called call. Turing machine's one calls, activates another Turing machine's T2 to perform a certain function using the same tape. The two control units using the same tape. You know, we are going to digress about that later on. Both using the same tape. So T1 provides T2 with the arguments, passes the control to the later to T2. T2 does the addition, right? Receives the addition and control from it, does the addition, and then calls T1 again to continue what it was doing, right? So every internal processing of a computer can do, this is very important, every internal processing a computer can do, a Turing machine can also do, right? Now, what a Turing machine cannot do, no computer can do. You understand why I'm presenting you with Turing machines, because it would be very complicated for me to explain to you how a computer works with the circuitry and so on and so forth, right? But I could explain to you how a Turing machine works. And now this is very important. If a Turing machine cannot do something, a computer cannot do the same thing. Now we understand what a Turing machine does, right, or is, and now we can examine what a Turing machine can and cannot do. You understand why I introduced Turing machines to you. So, but in fact, what a computer can do only manipulate discrete symbols, which can be associated to numbers because they always use a finite alphabet. And if it's a finite alphabet, I can associate the number 1 to the first, number 2 to the third, and so on and so forth. And I always have a numbering system, right, inside the computer. By the way, why are computer use the binary numbering system? Do you all know how to answer this question? Why a computer uses the binary numbering system? This is a very, very simple question to be answered. Well, and I'm going to illustrate that with my lamp here. Let's see if I can move my lamp. I have a lamp here. Now, you see the lamp is on, right? Now the lamp is off, on, off, right? Clear? Now I ask you the question, is the lamp off or on? Very simple to answer. You are seeing that it's off. Now I ask, is the lamp on or off? You all would say, now it's on. So it has only two states. So it's very, very simple and very fast to answer this question. I'm sorry, I have a dimmer, you know, I have a dimmer. I'm sorry. I constructed a dimmer with 10 different positions, and I could ask you the question, in which of the 10 positions is now the lamp? It would be very difficult to answer the question, probably with some mistakes, right? Because for instance, for intensity 5 to 6, the difference is very small. Now, if it's on or off, there is no doubt, it's very simple. So that's why computers use the binary numbering system, because the circuits are much simpler to detect if it's a 0 or 1, much faster, right? So it's just a technical convenience. Computers be using the binary numbering system. Some anthroposophists say, oh, you see, the computer is reducing everything to true and false, true and false, true and false. No, it could use the ternary binary, ternary numbering system. The Polish devised in the 60s, devised the computer which used the ternary system, -1, 0, and 1, for instance. It could use a decimal system. The problem is it would not be so efficient, just that. It's not necessary, technically, it's not necessary that computers use the binary system. It's just a technical convenience. This is, I think, an important concept, right? So any problem solved by computer has to be expressed as symbol manipulation, right? And a particular case is mathematical calculations. The first computers were developed, you know why? To calculate make ballistic calculations. You know, how to say, cannon, how to say, I'm sorry, cannon, well, throws some bullet, right? Some big bullet, right? And it makes a curve, right? And this curve can be calculated using the wind and the distance and so on. And these are the so-called ballistic calculations. And computers were developed for the war. That was the origin of computers. Later on, they began to be used for other purposes, but the origin was to be, they were supposed to be used in war. Right, okay. But the mathematical calculations, the mathematics has to be finite, discrete. It's not the general mathematics, like, for instance, differential and integral calculus. Differential and integral calculus, they have to be made with approximations to be calculated by computers, right? So it's impossible to represent the infinite or the continuum as the real numbers are. They constitute the continuum, right? Like the points, the dots in a straight line, they make a continuum. This is impossible to be represented in a computer, right? If the finite control of a Turing machine or computer program solve a problem, they describe an algorithm. So this is, for instance, how to understand what an algorithm does. Algorithm is something that can be introduced into a Turing machine or a computer and solve some problem. If it cannot be introduced into a Turing machine, it's not an algorithm, right? There is another condition also. All algorithms have to end at some point, their calculation, right? Otherwise, if it doesn't end, it's a semi-algorithm, but that's a technical thing, doesn't matter. So any use of a computer requires logical, symbolic, algorithmic thinking. Any use. If you use a computer, you are being forced to think logically, symbolically, algorithmically. even if one uses an iconic language. For instance, if you use a text editor, you want to justify a text, right? You activate an icon, you are using a symbolic language, a formal language, iconic language, right? So you are being forced to use symbolic language or an algorithmic language. You are forced to think in only those terms that the computer receives, accepts, recognizes, right? And not all kinds of thoughts, right? And this is terrible for children, but this is another lecture which I give very frequently. The impact of computers in education, right? Also for children, adolescents, and adults, right? Well, and I also have a special one for Waldorf schools, you know, where I show that the use of computers is absolutely anti-Waldorf for small children, also for adolescents. Only in my, I came to this conclusion many years ago. In fact, I published a book in English. It was, I don't even recall, by Flores books, you know, Computers in Education, you know, where I said that the correct minimal age should be 17. I could explain later on for you if you are interested during questions. I could answer you for this question. Why age 17 would be the ideal age to begin to use computers, the internet, and so on. Well, this is nowadays utopia. You say utopia? You know, it's almost impossible to prevent adolescents from using computers, right? And there is a big danger of algorithmizing the whole, the whole society, the whole world, and so on. Yuval Harari has written 3 books on that. You know, I have all of them. But I don't know if he understands could be understood exactly what an algorithm is, right? But he feels the danger of algorithmizing everything. So that means that means using computers for doing anything, not only just cognitive procedures or cognitive what? Issues. Okay, thank you. So I have to go fast. So how many, no, I'm sorry. How many types of instructions does a Turing machine have? That's a very interesting question. I've never found such a question in in texts or books that have chapters on Turing machines. By the way, give a look at the internet for Turing machines, and you'll see that they are described in a much complicated way as I have done, right? Well, yeah, I also used to ask people, you know, how many instructions do you think Turing machine, different types of instructions? Some people say 5, right? Remember the 5 tuple, you know, the state where the machine, the present state, the symbol being recognized, and so on. And they say 5, right? No, it's not 5, it's just 1. No, just one type of instruction, the ordered 5 tuple, as we have seen before, right? The present state, the symbol being recognized under the head, the symbol to be changed, right? The move, the head move, and then the next state. This is the only instruction type. And what a machine, like a Turing machine, using only one type of instruction can do. A PC or an Apple computer has hundreds of different instructions. For instance, addition of 8-bit numbers, of 16, of 32, of 64, subtraction, multiplication, division, and then of all of them. And then instructions to manipulate, to copy symbols from one place in the storage unit to another place, and so on and so forth. And also what's called floating point instructions, which use decimals and so on. Hundreds of instructions, but the Turing machine has only one type of instructions, not hundreds of instructions. I'm sorry, PC or an Apple has hundreds of types of instructions. And the Turing machine has only one type of instruction. Then one could answer the question, what could be done with only one type of instruction, right? This is a very interesting question. So what can be done with this single type of instruction, right? And here we come to the so-called Church-Turing thesis, which is also formulated in another way. This is a simplified way. If there is an algorithm to calculate a mathematical function, this function can be calculated by a Turing machine. That means the Turing machine can calculate any, absolutely any mathematical problem that is described as an algorithm. The solution is described as an algorithm. And in this case, the Turing machine can solve that problem. So it can solve any mathematical problem described through algorithms. And this applies also to computers, right? That means the Turing machine, I'm sorry, it's not MT, that's the initials in Portuguese. This is 50, slide 50. Okay, that is a Turing machine, with a Turing machine, one can do any internal computer data processing, because this is equivalent to calculate a mathematical discrete function. Computers are mathematical machines. What they do is they manipulate symbols, calculating, any command one does to computer. For instance, the icon, if you press the icon or activate the icon with your pointer to justify a text, right? What it does, it activates a mathematical function of manipulating symbols to justify the symbols to the right and to the left. It's a mathematical function. Computers only use mathematics, right? Okay. Therefore, with only one type of instruction, it allows the execution for any data processing. That's surprising, right? And this is one of the essences of computers. And another interesting thing is that there is no abstract digital machine more potent, with more power than the Turing machine. One say that any variation of the Turing machine can be proven to be equipollent. That means has the same power to the original Turing machine as I introduced to you, right? For instance, a Turing machine with 2 tapes, a final control using 2 tapes. It's very simple to demonstrate, formally demonstrate, that there is original Turing machine that is equivalent to this one, right? So any variation of a Turing machine, always with finite control and infinite tapes and so on. Any number of finite controls, by the way, with 1 tape, for instance, or more than 1 tape, doesn't matter, as long as they communicate. They don't have more power than this Turing machine that I presented you. That's very interesting. Any variation for instance, here one has a Turing machine with 2 finite controls using the same tape. And in this case, the transitions must be sextuples. That means there would be another symbol specifying if the control should jump to finite control 2 or back to the 1 and so on and so forth, right? Okay, in this way, one could have a finite control to do additions, for instance, right? So if it would be necessary to add two numbers, well, this finite control could jump the control to the finite control 2, and this finite control 2 is specialized in adding two numbers. You understand? But this doesn't have more power than the regular Turing machines. And now a very, very important concept that will be essential for the philosophical questions that will come a little bit later, right? Let me see, I have a half hour, a little bit more than half hour. My goodness, let's see what I can do. Well, what is the universal Turing machine? It's a Turing machine U. I have used symbol U for that accepts on the tape the description of a Turing machine T. How? These 5 tuples, right? The sequence of 5 tuples of the final control of a machine T, right, is used by machine U, whose finite control interprets the sequence of transitions described machine T. So universal Turing machine is a simulator of any Turing machine, right? Receives a description of a Turing machine. That means the sequence of transitions plus which is the initial state plus what are the final states, and it begins to, and also some input data, and it begins to interpret that machine using that input data. You understand? So this is the universal Turing machine, a very, very important concept, okay? So, and now thinking about computers, giving enough data storage capacity and processing time, any computer can simulate any other computer. Right? Computers are universal machines. Any computer could be programmed to simulate another computer, right? This was done years ago when another machine would be developed with a different instruction set and so on. A program called emulator would receive the machine language, the most basic language of a computer, and would interpret it and execute the same thing as that previous computer did, right? So computers are universal machines. They can simulate any other machine. This is another fundamental essence of computers, that they are universal machines. And now comes some philosophical considerations. Is the human being universal or individual? Andrew is signing so. What does this mean, Andrew? Universal or individual? Oh, probably all anthropologists would answer individual, right, Andrew? So humans are individual beings, not universal beings, right? We cannot simulate another human, right? Now let's consider what it means. Thoughts can be objective and universal. For instance, all mathematics is universal and objective. If I think on a geometric dot point, right? And I tell you, I'm thinking about the geometric ideal point with no dimensions, right? An infinitely small point, right? That cannot be represented. Any representation is finite. But you would think on exactly the same concept of a dot, right? If I tell you I'm thinking of a circle, you would think about the same thing, the same properties of circles, that are the geometric locus of all points equidistant to the center, right? And these are all objective and universal concepts. So we are able to think objectively and universally on universal objects like mathematics, whole of mathematics, right? Or a correct concept behind a correctly perceived object. For instance, if I would point to the object at the entrance of this room, this object here, right? And I would ask you, Andrew, what are you visually perceiving at the entrance of this room or your room? What would you answer, Andrew? What are you visually perceiving? Can you answer?
A door.
A door. And probably everybody would say a door, but you are all wrong. You are not visually perceiving a door. You are visually perceiving visual impulses, light impulses. You are not perceiving a door. Door is a concept. Andrew, you didn't describe that door. It's white, it moves around, I don't know how to say, hinges or whatever, you know. You said a door. That means you recognize that that object is of the same Aristotelic category of all doors. You express the concept, not the particular door, right? And you saw, that's why I asked visually perceiving and not seeing, because when one uses the word to see, one is already implying the concept of what one sees, right? Now, that object, the concept of that object, the door, is all of this the same for everybody. Nobody would say that these are diapers, right? This is a door, right? Right? It's the same concept. So we reach we can use universal and objective because it doesn't depend on any of us. Everybody recognize the door, not diapers or a window or whatever, right? So behind every object, there is an essence of that object. So we can be universal when we are speaking about concepts, about ideas, right? And this is very clear in Rudolf Steiner's The Philosophy of Freedom, right? If one wants to see a very nice abstract of the philosophy of freedom, give a look at Frederick Emrein's, oh, I forgot the name of the book. It's the foundation.
Foundation of the Valdemar.
No, that's the subtitle, foundation, the philosophical foundation of Waldorf education. Kicking Away the Ladder. That's the name of the book. Kicking Away the Ladder. Okay, he has a chapter which I translated into Portuguese. By the way, I translated the whole book. It's being print. Kicking Away the Ladder, right? Well, he has a very nice abstract of the philosophy of freedom. Okay. So the question was human being universal of individual. So we saw that we have some universal and objective activities in our thoughts. Now, if I think about something on myself, for instance, I have some pain, all right, pain in this thumb. I had some days ago, you know, I got pain here. If I think about this pain, I'm not thinking objectively. I mean, or something objective that can be thought of by anyone, right? Because it's my own pain, right? But we can think objectively and universally when we think about concepts, which is the case of mathematics and so on. Now, there are things that are not universal and objective. Sensations, for instance, and feelings, right? And here I give an example. Andrew, how to say, forge, represent that you are eating an orange, Andrew, eat an orange, Andrew.
Yeah.
Yeah? Show that you are eating an orange. Good, excellent. What is happening? Andrew is feeling the sensation of the taste of that orange, right? Are you feeling the taste of that orange, Andrew? Yes, you are. So, yes, so this is what I call a sensation. You know, taste is a kind of sensation, right? And this is absolutely individual and subjective. Why? When Andrew is eating the orange, he's feeling the taste of that orange. I cannot feel the taste he's feeling. Nobody can feel the same taste. Only he is able to feel that taste. You understand? Nobody else can feel a sensation. It could be, for instance, cold or warmth. Right. Suppose it's very cold and Andrew is, you know, is freezing with the cold and so on. Nobody else can feel the cold that Andrew is feeling. You understand? These are sensations. Or fear, for instance. You know, there are many sensations. It's also, Andrew, it's impossible to describe the taste of an orange to somebody that has never eaten an orange. Try to do it. It would be impossible. You could say, well, it's a little bbit acid, but that's not the taste of an orange. It's a little bit, how to say, with sugar, sweet, yes. It's a little bit sweet. This is not the taste of an orange. So you see, this is something that sensations are absolutely subjective and individual. And when Andrew eats the orange, he either likes it or dislikes it. If the orange is ripe, very sweet, he will like it. If it's not ripe, if it's green, right, very acid and so on, and Andrew doesn't like lemons, right, he is not going to like the orange, correct? This is what I call feeling, right? The feeling is a second kind of internal reaction. The first one is the taste, is the sensation, and the other one is liking or disliking, right? And nobody can have the same feeling as another person, right? But it's interesting to realize that there are more basic feelings like sympathy or antipathy. If Andrew liked the orange, he had sympathy for the orange. And more basic is the attraction or repulsion. If Andrew liked the taste of the orange, he had an attraction to the orange, right? Or if he didn't like, he had an antipathy or repulsion for that. But the important thing is that sensations and feelings are absolutely individual and subjective. So human beings, in the sense of sensations and feelings, are individual and subjective beings, right? Now comes a very, very important conclusion. Machines are always objective and universal in terms of computers, right? Digital machines. So they will never have sensations and feelings, because sensations and feelings are individual and subjective. And these machines are not individual and subjective. It could be, it could be, for instance, a refrigerator. Refrigerator has no individuality. If you put if you have these two refrigerators of the same model, same date of fabrication and so on, of production and so on, and you put the dial on number 1, right? They'll have slightly different temperatures, but this is not individuality, right? They had the same project, the same design, the same construction, and so on. So they are not individual in this sense, right? But humans are absolutely individual and subjective in terms of feelings and sensations and some kinds of thoughts, right? And other actions, for instance, dreams. You know, dreams are absolutely subjective and individual, right? So humans have lots of individual and subjective characteristics, capacities, and so on. but machines don't. So machines will never have sensations and feelings. So the films Artificial Intelligence by Spielberg and Bicentennial Man by Columbus are wrong. You know, both use represent robots. Artificial intelligence was a boy robot. A Bicentennial Man, Robin Williams represented a robot, and I don't have time to describe them. I could. There are very interesting messages behind these films, right? Also, absolutely some absurdities that are terrible. I dislike, I don't like at all science fiction films because all of them have some physical absurdities, like in Artificial Intelligence, that a boy robot stays under the sea for 1,000 years. The batteries don't last for 1,000 years. He doesn't get, how to say, rusted, rusty, and so on. Well, anyhow. So recall how we began with the Entscheidungsproblem, the decision problem or decidability formulated by David Hilbert. Every well-formulated mathematical problem can be solved. With the Turing machine, Turing proved that there are well-formulated mathematical problems that cannot be solved, that they are undecidable. How did he did that? He proved that there is no universal Turing machine that interprets another machine, examines another machine, and comes to the conclusion that that other machine stops or never stops for any input data, right? If it's going to stop or it's not going to stop, it goes into a loop. It's going to repeat, you know, instructions and so on. And this is what is called the famous halting problem. If you put halting problem on the if you do a search on the internet with the halting problem expression, you'll get to that. Well, so what is the halting problem? Here I described textually. You can read it if you download it. And here I have a description, a graphical description. It's very simple, but has a very, how do you say, very trick, a very special trick, right?
Tricky.
What?
Tricky.
It's very tricky. Anyhow, suppose machine, we have a machine T2, Turing machine T2, with this tape. You know, I have three moments of this tape, and it receives the description, the final control description of a Turing machine T1 as an input. And as an output, this machine examines the description of T1 and gives either, it writes on the tape, either that T1 stops for any input data or T1 doesn't stop, for some input data, doesn't matter which, right? Either it doesn't stop or it stops. So these are the two, exclusive outputs of that T2. T2 examines T1 and gives us output the answer T1 stops or T1 doesn't stop. Right, okay. Now, suppose there is another machine T3, right, which produces, the T3 and T2 uses the same, they use the same tape, right? T3 produces into the tape the description of that first Turing machine T1. So it writes into the tape, on the tape, the description of T1, which is read by T3 in the, oh yes, before that, T3 kicks T2, activates T2, which reads then the description of T1 and it's the same as this one. T2 is the same one. So it examines T1 and produces an output. T1 stops or T2 doesn't stop. But then it kicks back T3. T3 assumes the control and it reads what was written in the tape, either T1 stops or T1 doesn't stop. If it reads T1 stops, it goes to the initial state, jumps to the initial state. If it reads T1 doesn't stop, it stops, right? It goes to a final state without any transition from it, and it stops. Now, here is the big trick. We make T3 describe itself into the on the tape, right? It produces its finite control textually, and this description of T3 is read by T2. T2 decides if T3 stops, writes here T3 stops, or write T3 doesn't stop. If it writes T3 stops, and then kicks back T3. T3 assumes the control, reads what was written, and goes to initial state. Aha! If it goes to initial state, it doesn't stop. It begins all over again, right? Produces again itself, you know. So T2 decides that T3 stops, but it doesn't stop. If T3 would have read T3 doesn't stop, it stops, right? This was the way T3 worked, right? So this is a contradiction. With this contradiction, Turing showed that the T2 could not exist. So there is no possibility of a computer. I'm going to generalize. There is no possibility of a computer examining some program, you know, written for another computer or the same kind, and deciding if the program is going to stop for any input data or would not stop for some data, right? This is the famous halting problem, which is applied also to computers, right? So this is also true for computer programs. There is, as a computer in this program is a restricted Turing machine, right? So if the Turing machine cannot decide if another Turing machine stops for any input data, and a computer cannot, or computer with a program cannot do the same thing, right? But there are also problems that computers cannot solve. For instance, there are problems that there are no efficient algorithms. These are the so-called intractable programs. For instance, problems that take a time, an exponential time. For instance, suppose we have a time 5 to the power 5. This means multiplying 5 times 5 by 5 times, right? Power 6 times 5. So increasing the number of input data, if a computer program would take an exponential time, I had 5 pieces of input data. If I changed to 6, you know, it's an exponential time, and this is a disaster. An exponential time explodes in time, right? But factorial is even worse than exponential, because exponentials multiply always by the same number. You know, 5 to the 6 is one more time times 5. But 6 factorial, now I multiply by 6, which is bigger than 5. So any problem, any program that has a computer time proportional to the factorial or exponential of the number of input pieces, right, is a disaster. And these are the intractable programs. I could give you some examples if you wish. Anyhow, I have only 10 minutes, my goodness. So can machines be intelligent? And I have to describe what the Turing test is. Well, this depends on the criterion of intelligence, right? And I wrote a paper about that, and not just a paper, also a book, which was published by Frederick M. Ryan at his publishing house, Carrick's. The name is AI, Artificial Intelligence or Automated Imbecility. Can machines think and feel? I'm describing what is in that book, right? And one of the chapters is on intelligence, right? Is a master chess player an intelligent person, right? Depends on the definition or the characterization of intelligence. If one says a good chess player is intelligent, then the computers are more intelligent because nowadays we have programs that are, how to say, cannot be. Oh, I'm sorry, I forgot forgot the word. Cannot. My goodness. Well, anyhow, it's not a criterion. So because how many intelligent people don't play chess, right? So playing good chess is not a good criterion. So Alan Turing suggested what he called the Turing test in 1950. And he called it the imitation game. And the imitation game was the following. A person had to discover by making questions and receiving answers if in a room there is a man or in another room there is a woman. He would have to discover who is the man and who was the woman, right? With one rule, the woman would always answer correctly, but the man could cheat. So at that time, 1950, all women were honest, right? Okay. O que você falou? Well, so he called it, now he changed that for one person using a computer terminal, it was a teletypewriter at that time, and typing questions to either a machine, a computer, or to a person, and would receive the answers, right? And he would have to discover what is the machine by the answers, what the is machine and what is the person, the individual, the human person, right? This is the imitation game, the name of that film that had nothing to do with the Turing test. It was about the Turing, the machine that decoded the Enigma German machine during the war, right? So the film title was wrong, but never mind, okay? And there is an annual competition, the Loebner Prize competition, and the Loebner Prize gives a prize to the program that gets as close as possible to passing the Turing test. And you can test that program. I did that. I'm going to show you now. But I wanted to say that there is no hope that the program will pass the Turing test. There is a book by Ray Kurzweil. I'm sorry, I wanted to bring the book and I forgot. I have it here. It predicts that in 2029, there will be computers passing the Turing test. Now let's see what the program that won Loebner Prize for 2013 and from 2016, including 2019. And here is the link to that program. So I tested the program. Here's my test. The program is called Mitsuko, right? It's a Japanese program. So I use the program. Everybody can do it. It starts. The program says hello, and I made the question: do you know where the Wonderland is? And now the question was surprising. I thought it would give a wrong surprise, but this is I'm sorry, the wrong answer. But it gave the correct answer. It is in a book by Lewis Carroll, where Alice goes. Excellent. But then I made the question: in what continent is Wonderland? And look at the answer. I have not heard of the country, but there are lots of countries in Africa, so I will guess at that. So absolutely wrong answer, because it's a fantasy. It doesn't exist as a country in Africa or wherever. So you see, in two questions, I discovered that it was a machine and not a human that would, an intelligent human with enough culture. That's a very important point. That would answer the correct answer, right? So you see, this is the Turing test. But Turing was essential to Germany's defeat in World War II because he decoded the German Enigma coding machine. I could describe some of the terrible decisions the British had to take so that the Germans would not discover that Turing had decoded the Enigma machine. Terrible things. I could describe some of them if somebody is interested. Write down and I'll answer later on. But it had nothing to do with the Turing machine, you know. It was based on a statistical study of the frequency of letters and syllables in the German language, right? But interesting thing, Turing himself, with his life, with a tragic end, he had a tragic end in his life. He committed suicide. He showed that logical mathematical intelligence, he was a brilliant mathematician, right, and logician. It is not essential from the human point of view. Why? He didn't have common sense, social intelligence. Why? Because he was homosexual, he was gay, right? Which was forbidden at that time in the 1950s in England. And he had a boyfriend. But this boyfriend, robbed 10 pounds from him. So Turing went to the police department and accused his boyfriend of having robbed him. And the police department discovered that he was gay. And this was not allowed. So he was condemned because he could not reveal that he saved the world from the Nazis, right? In the World War II, it was essential for that. He could not say because it was a big secret yet. And then he was condemned. He had to take hormones and so on and so forth. He got mad, he was depressed and so on, and committed suicide. So you see what I wrote a paper about that, Alan Turing, computer science, because there was a theater play about Alan Turing called Turing, or the imitation game, I don't recall anymore. But and they asked me, the producer asked me to write a paper, a small paper about for the program about Turing. So I did that. But it's unfortunately I didn't have time to translate it into English. But if you use a translator like Google Translator or DeepL, as somebody has written here on the chat, you can read it certainly. Anyhow. And for Turing's life, there is an excellent book, extraordinary book. This one, Alan Turing, by Andrew Hodges. It's very thick. Here's my hand. Here's the book, right? But it's very, very, very interesting, very detailed book. Okay. Well, also with his life in the Institute for Advanced Studies in Princeton and so on. So. Well, I have only 2 minutes. Well, further philosophical consideration. Can computers feel? As we have seen that already. Computers will never have sensations and feelings like human beings. Never, according to my reasoning. Can computers think? Now, anyone may have the experience of concentrating the thoughts, right? Determining the next thought. For instance, you choose mentally choose 2 numbers that have no significance, 2 numbers with 3 digits, for example. You imagine one of them written somewhere in a display, for instance, and another one, and then the first one and another one, and then you choose one of them, like the first one, right? And think only about that one. So you are making a free choice, and everybody can experience that. It has to be experienced by everybody, that you can choose between 2 things that have nothing to do with your previous experience or your necessities, right? Like any numbers that have no meaning whatsoever, right? So we're able to determine the next thought, right? And this is free will. And this has to be experienced. It cannot be proved. Everybody has to experience by him or herself. So if it would be an illusion, we could not control our thinking and would not trust our thinking. We are able to determine our next thoughts. So a strong conjecture is that computer will never have free will. Why? Because they follow physical laws and conditions and program. They are deterministic machines. In fact, not fully, because sometimes they crash, right? Mainly when they are running Windows, there is a bigger possibility of crashing, right? But imagine if computers would have free will, sometimes they would give 2 plus 2 equals 4, and sometimes they would give 2 plus 2 equals to 5. It would be a disaster. Computers have to be deterministic machines, right? They cannot have free will, right? And our thinking is much more than what can be expressed in programming language. For instance, I have already described the infinite, or the continuous, or a pure geometric circle. If a computer would draw a circle, it would be drawn by dots, right? Discrete dots, right? And not what we can think about the perfect circles, right? Circle. So, and thoughts imbued with feelings and so on. Computers cannot have that. So one can make this strong conjecture that computers will never think like human beings. Never think like human beings. That's my conclusion from the considerations that I have made. Well, speaking about the infinite, I wrote a book about the infinite. Unfortunately, it's only in Portuguese. It's online. It's an ebook as well. This picture was taken by one of my grandchildren, Tiago, in New Zealand. You see how the street sides are going to the infinite. Anyhow, but you can eventually translate some of it, right, from a book. Maybe I'll translate it into English, but I have so many things to do. So computers will never do everything that humans do. But the converse is also true. Humans cannot do everything computers do. For instance, a large amount of symbol manipulation, including calculations, of a reasonable amount of time. So I'm going to finish. I wanted to describe something about the Sophia robot. This robot expressed terrible things about robots in 1917. For instance, foreseeing a harmonious future between robots and humans, that robots would have transcendental power, intelligence, and would not have problematic emotions, would have emotions, which is absurd from my point of view, but they would not have problematic emotions like humans, and so on and so forth. It's such a stupidity that is terrible. And it was awarded a Saudi citizenship from Saudi Arabia. Can you imagine something like that? How deep how deep can humans fall? Assigning citizenship to a robot. Anyhow. Then I would speak about technological singularity and man-machine symbiosis. All this is just something about symbiosis. For instance, people say someday we'll be able to download our memory into a computer or upload what is in the computer memory to our memory. This is such a stupidity, to say. Why? Because it would be necessary to know what code the brain uses. But this is not known. I have shown you that one doesn't know where the symbol for 2, the number 2, is written or stored in our brain, right? The simplest thing, one doesn't know how the brain. One knows how it works, some detail, but one doesn't know what is the correspondence to feelings, to thinking, and so on, to memory, and so on, right? So it's in my conjecture is that the brain does not use a code, a numeric code, as computers do. So it's not possible to download something in our brain storage, right, to into a computer and converse from the computer there, because it would be necessary to know. So know this code. So my conjecture, which is very strong, is the code of the brain will never be known because it does not exist. And from anthroposophy, we know what it means, right? What goes on in the nerves, right? They make a kind of empty space, right? And so forth, thinking and so on. But then that's another thing. Unfortunately, I didn't have time to go into my theory of how something that is not physical, like the spirit or the etheric body, can act upon the physical matter, right? Because you see, the spirit doesn't have hands, doesn't have fingers, to manipulate the physical matter. How is it possible? I use for that the concept of non-determinism. That's why I introduced the non-determined. Oh no! I was going to do that next. Non-determinism in the Turing machine is you are in the machine is in a certain state, but there are two transitions with the same input symbol. So it could be make a transition to there, or make a transition here to another state, or make different movements, or make or write different symbols on the tape. This is mathematical non-determinism. So my conjecture is that we have lots of non-determinism, physical non-determinism. For instance, in cells like this, a cell could be in a state, and in the next instant, it could be in the same state. It made a transition to the same state. It stays as it was. It makes a transition to a state where it begins to subdivide into two, or it begins to die, apoptosis. Here is meiosis or mitosis, right? So I conjecture that there is a physical non-determinism here. So something that is not physical can choose what transition is going to be taken the next instant. And this choice doesn't require energy. It's just a choice. And these explain how our hands, when we were born, the hands were small, like this, right? And when I grew, I grew up, then the hands grew, but they preserved the symmetry. Your hands are symmetric. How is it possible if the growth is due to cell division, or some cells die? Every 7 years we change all the cells, but we remain the same. Why? Because there is a model deciding which cell is going to divide, right? The model implies chooses which cell is going to, which cells in a tissue are going to divide or die, and it's controlling the growth this way. That's why we are so symmetric. And look at this. Look, this plant is extraordinary. That's the cheese plant, which is called Adam ribs in Portuguese, costela de Adão. It makes always the same figure, in the parts of the leaves. These are parts of the leaves, but they make the same curve. Look at these. All of them have almost the same shape of this curve. How is it possible if every part of the leaf grows independently of the other part, right? Why? Because there is a model. And we know where is this model from anthroposophy. That's the etheric body, right? Or in humans, the phantom, right? Look at the symmetry of this butterfly that I took a picture, right? In a beach, 200 kilometers from here. It's the symmetry is absolutely extraordinary. How is it possible that the cells were divided, preserving the colors and the symmetry of colors and forms and shapes? It's absolutely, it's not possible that a cell here would, on the right side, would divide, would assume a certain color and tell the corresponding one, you have to do the same thing, otherwise you break the symmetry. There is a model imposed. Also, the body is symmetric. Look at this. Look at the figure of the body. Well, well, this is my theory. How I'm sorry for being already 10 minutes later. And the answer, one can come to the conclusions that human beings are not purely physical. They are not machines. So there are very strong evidences. I gave you some. Well, I would digress into materialistic science and so on very briefly, but doesn't matter. I'm going to finish, right? This is the end. And please, after I I make the form, the assessment form, please fill it up. I'll send Andrew the address to the form. Please fill up the form. I would very much like to see your reactions. And also, I'm going to copy all of your assessments into the page on my website, and you'll be able to read what the other people answered, and eventually my comments on your answers, right? So this was the lecture, and I have to thank very, very much and excuse myself for being 10 minutes later. I told I had to take 2 hours for the lecture. You see, there were so many things I wanted to express. Always when I review a presentation, I review it with the intention of shortening it, but I always end up enlarging it. I'm very sorry. Now I'm going to stop the share, and I'm here at your disposition. I don't know how to say that in English, for questions, and eventually go into detail in some of the points and so on. I don't have any time limit. It's already 11:42 here p.m., but it doesn't matter. When I give a lecture, I become very excited, very enthusiastic. So I have absolutely I'm not sleepy at all, not sleepy. So I can stay here as long as you wish.
So we, first of all, want to thank you very much, Valdemar. You've kicked off our webinar series spectacularly. And I've seen some comments from people. There are a couple of questions. And so let me read one of these questions for you. And oh, by the way, I share many of the issues. I'm known to give lectures, and I say it'll take 45 minutes to, or I'm told 45 minutes to an hour, and I take 90 minutes or more. So we have this problem. It's universal for some.
Yes. Somebody asked for the slideshow. So yeah. That's, I have already repeated the address. Please copy it into a text editor, and then later on you can immediately, how to say, press it or activate it and get to the slideshow.
Go to the chat and copy and paste is what he's saying from the chat.
Copy and
the link
paste.
Is there. And yes. I will have it as well. Okay, so what is the significance between the difference of Turing machine universality and the conceptual universality? Okay, so in parentheses, he said, in the Turing machine universality, as described, is the possibility of infinite simulation or repeatability, and the other conceptual universality, sharing of one and the same thought by many or by all.
Yes, I showed you that we are able to repeat some thoughts thought by another person. If this person thinks about some concept, like all mathematical concepts, we can repeat them. We can think the same thing. it's even more than that. You see, we reach the same concept in the Platonic world of ideas, in the spiritual world. It's even that. So in this sense, we are universal. But what I wanted to show is that we have activities, we have capacities that are absolutely individual and subjective. They are not universal. Like, feeling the taste of an orange. That's absolutely individual and subjective. So we have capacities that are not universal. In fact, I have in another lecture a citation by Hogland, famous artificial intelligence researcher, and he expresses his astonishment, right, when he thinks about sensations and feelings. He says, as long as I think about sensations, I don't understand them. As much as I think about them, I cannot understand what are sensations, because he's thinking physically. And from the physical point of view, he's materialist. He's a materialist. From the physical point of view, sensations and feelings have no sense. We experience them, but they cannot be described scientifically, formally, right? Okay, and he expresses this surprise. What are in fact sensations and feelings? And he adds, it's not important that, I don't say that they are not important, right? I say that I cannot understand them. And it's very interesting that in the philosophy of freedom, Steiner has a paragraph where he says that exactly sensations and feelings make us feel as individuals. He says, if we would be just cognition beings, right? Cognitive beings, ourselves and the world would be absolutely, how could I say that? Would have no importance. You understand? We assign importance, we assign significance, and so on to ourselves and also to the world. When not significance is not a good word, because significance is the concept, right? To understand it, to reach is reaching the correct concept. That's what I express as understanding. But so he says that feelings and sensations are absolutely essential because they make us feel as individuals. If we would be just cognitive beings, we would assign no importance to ourselves. I don't know if I have answered your question, Andrew.
Well, it's not my question, but that was from Jonathan.
Oh, I'm sorry, I understood it wrongly.
Yeah. Oh, I'm reading the questions for the recording. So another question here has to do with this eating the orange. And in this question, if we were to take the orange and I were to split it up and I was to eat some and hand it to the person next to me and they were to eat it, we'd have a shared experience kind of the orange. Now, I remember in Boy Scouts, we used to question, okay, so it was a shared experience, but did we actually taste it the same? Did it taste the same to each of us? But, and how do we know that? So he goes on to say, we refer to an objective non-sensation to indicate a nameable sensation. Is this not what the Turing machine does? That is, who is to say a sensation is not had during Turing machine symbol indication by an individual unknown to us? I'm not sure I quite understand the question, but.
Look, first of all, You can eat an orange. Give me a piece of your orange, Andrew. Okay, I got it. You eat your orange, your piece, and I eat my piece, right? Are we feeling the same sensation?
Right.
No, no. But if I tell you I am thinking about a circle of radius 10 centimeter, well, you're going to think exactly the same thing, the same concept. But I'm going to have my feeling, my taste of that orange, and you have your taste. Now to the Turing machine. Suppose a Martian, a person from Mars, would come to the Earth and would miraculously speak English. Now, Andrew, go to the Mars, to that person from Mars and try, and he has never eaten an orange before. Try to describe him the taste of an orange. Absolutely impossible. Impossible. So how can you describe the taste of an orange as a Turing machine? You know, writing on the tape some symbol and so on, describing something that is undescribable.
Right.
Does it answer the question? So we cannot insert feelings into a Turing machine or a computer. What we can do is the psychometrists do. What they do, they say, let's assign -5 to a very acid taste and +5 to a very sweet taste, right? So we have a range from, and ask everybody to eat a piece of orange and classify from -5 to that's what to +5. That's what is called psychometrics, right? In psychology. But these are not, the sensations have nothing to do with sensations themselves, you know. It's it's a figuring out, you know, something that is absolutely subjective, one could get some feeling for what a person says or finds. For instance, if it's -5 or +5, we would immediately understand that it's very acid or very sweet. But he could have said it's very acid, it's very sweet, or it's a little bit acid or a little bit sweet. These, are not the sensations themselves, right?
Eu gosto de sweet e você gosta de acid, então nós vamos sentir diferente.
Yes, my wife is saying she likes sweet and I like acid, so we are going to like differently, right?
So I have another question for you.
Yes.
And that is, there are, in Japan especially, friendship robots. And these robots have software that, the expert that was used was a psychologist on how to respond with feeling. And so you might call it, as we have artificial intelligence, you might call it artificial feelings or artificial soul. And apparently some people like these. So I don't know if you can comment on those, but is there any reports that you know of that people get rather bored with these after a period of time? Or what being reported only the initial response?
Yes, because the storage is limited, and well, the robot could combine, words and so on. Now, well, let's put it this way. Are there other possibilities? Are there possibilities that an old person could have a human as a companion, right? Some hours and so on. If this is possible, this would be much more preferable, because we know from anthroposophy that what happens between two people are not just what these people exchange in words, are much more. And it's easy to understand, the gestures, the attitude, and so on. And I'm absolutely sure that if a robot does that, we can immediately feel that it's artificial, it's not human, right? Something is lacking. Now, from anthropology, we know that in human relations, there are other things than just words or actions, So now, if there is a possibility of having a human being a companion, I think this would be much more preferable. Now, suppose there is no possibility. For some reason, there is no possibility. In this case, maybe the robot could be, could eventually do the job not very well, as a good human companion would do, but at least something. So this is all quite relative, I would say, right? It's the same thing with classes, right? If it is possible to have a presential class, it's much more preferable than a virtual remote class, right? Remote lesson, right? But there are situations when a physical presence is not possible. For instance, an adult wants to learn something, participate in some class, but he lives, miles and miles away in the other part of the continent, right? In this way, at least the virtual class is something already. You see, so it's one has to take into consideration many situations. Humans are not strict formal beings, so one always has to take into consideration the situation of each case. There is no uniform solution for anything in terms of humans.
Yeah.
Did I answer the question? Did I answer the question?
Yeah. So one last question here. If you could comment about implants, the brain-computer interface.
Yes.
And what, so just your comments about that. As you probably know, Steiner mentioned something a couple times about how in the future there will be a second being with us. And it will whisper in our ears, or give us direction that's materialistic, because that's all it can do. And it'll be with us from birth to death.
Well, according to Steiner, there is the what is it called, Sonia? The double,
Harmonic double.
The harmonic double. It exists from birth, right? And it's very interesting that some people are near death, right? And 3 days before they die, this double gets out and the person has an improvement, right? In 3 days later, this person dies. Well, I tried to show that in my way of thinking, my conception, there is no code interpreted by the brain. The brain doesn't use a code. It is not known. And well, you could say, but how is it possible that with a helmet, an electrical helmet, right? Waves are detected, electrical waves are detected, right? Or in apes, chips are inserted, detecting the the actions of a set of neurons, hundreds of neurons, right? It's a matrix. It's a matrix of the sensors, detectors, and these goes the helmet or the sensors from in the ape they go to the computer. The computer interprets that, and some action is taken. For instance, mentally moving a pointer on a screen, or the legs of a robot. This was done with the ape by Nicolelis, Miguel Nicolelis, a Brazilian that is in Purdue, I think, or something. I don't recall exact. Dartmouth, no, I don't recall which university. He's in the United States. Well, what is happening? Is the computer recognizing the impulses detected by the helmet or the chip? Yes, it is receiving these impulses, and it is transforming the impulses into a movement of a pointer on the screen or the movement of legs of a robot, right? But one does not know what those impulses mean. It's a purely empirical thing, you know. I read Nicolelis' book, you know, much translated from Portuguese, much farther than the I. That's the translation into English, right? His book, where he describes these experiments, what he did with implanting chips on the brain of an ape and so on, of a female ape and so on and so forth. But he doesn't tell how the program works. And I presume that it's what's called linear regression analysis. Linear regression analysis is taking numbers, right, graphics and so on, and transforming it into a curve, into a function, into a mathematical function or a set of functions. And that's, I think, what he's doing, right? He's transforming those impulses into some functions, and empirically, right, he got the possibility of, for instance, the function of moving a cursor on the screen just by the person thinking about this movement. But he doesn't know what the impulses mean, right? And how the impulses are produced. I'm going to give you an example. Andrew, please, you are my victim because you are the only one I'm seeing. Show us how you lift your arm. Lift your arm. Yes, good, excellent. Andrew, how did you lift your arm?
Raise your arm.
You raised your arm. Suppose he's pointed to his brain. Good. Suppose your brain sent some electrical pulses, right, to some fibers, muscle fibers in your arm. Some of them contracted, some of them expanded, and your arm was raised. Fine, okay. Suppose there was an area in your brain that sent these impulses. Can you buy that? Okay.
I don't, but you can say it.
Okay. Now, suppose now you ask the question: how come area A has sent these impulses to the fibers, muscle fibers? Now, suppose there is another area B that sent impulses to area A, which sent impulses to the fibers, muscle fibers, and the arm raised. Excellent. Now, how come area B sent the impulses to area A? So if you continue in this cause and effect sequence, you always get a dead end. Always. It's impossible, right? That you get to some place there that originated by itself. It has some, so from somewhere, anything that would originate impulse had to have some origin for it. Would it be itself, for instance, area A would itself generate without having an impulse? How come could it generate by itself? Something has to, something has to, how to say, to push it,
Initiate.
and that's not physical. So I have a conjecture. If you take any internal action of any living being, it could be a plant, right? If you ask the cause of some internal action, like for instance, sprouting, or another branch or a flower or whatever in the middle of a branch, right? If you ask the question, what is the physical reason for that? Maybe you find some, but then you ask the question, what is the reason for the reason, right? You always get to a dead end, right? It's impossible that physically we get to a place that the thing itself decided. How come a thing, something in ourselves or in a tree can decide, suddenly decide to take some action? Impossible, right? And we know how what goes on. That's the etheric forces that do that, right? And they are not physical. And now we come to the explanation, to the theory I explained about the non-deterministic transitions. So if there are non-deterministic transitions involved there, something out of the physical can decide what transition is going to take. So there could be some neurons in some states, and suddenly they fire. Why? Because something outside the physical decide that they should fire, because they could fire or not fire. In fact, it is not, if a neuron is examined, sometimes with the same input, the same impulse that goes to the neuron, sometimes it fires, sometimes it doesn't fire. So each neuron is non-deterministic. And there, something that is not physical can determine if it's going to fire or not. That's my theory. I have described.
It's interesting that with, you were mentioning robots, there's also prosthetic limbs that people are learning to use, amputees, where they can move this and they're told they're moving it with their mind. But in all cases, that person had to have once had a real physical limb that they could move. And so they're being told, move your phantom limb. And over time, this prosthetic limb and the senses in the, whether it's a skull cap or something implanted in the nerves or whatever, you get to get closer and closer towards the original behavior of that phantom limb and moving it.
Yes.
So it's fascinating bringing up, yes.
Yes, I'm not against that. It's great that there could be an artificial limb, right? If a person doesn't have a limb, it's great that there could be an artificial one, and the mind could eventually move, right, that limb. But I think this is not so simple. Why? Because our thinking, right, our feeling and so on, in general, we can determine some of them for some instance, right? And it takes a long time meditation, right? So that one can control one thinking for a certain period of time, right? Because in general, if one starts to think, concentrate the thinking on some subject, suddenly other thoughts come into play, right? And how will it be possible, to move the limb without thinking in another thing, in other things, right? So I don't think this is so simple, right? But if it again, the most important thing that one does not know how the impulses are generated and what they really mean. It's empirical that it's great that it may work. I'm not against it at all. I'm against replacing actions, human actions that could be done by humans.
Right.
We have a famous author, Rui Barbosa, in the beginning of 20th century. He said the profession that most elevates a human, right? Is that clear? Elevates a human is teaching. Teaching is the highest profession in terms of, in human terms.
Mhm.
And this is being replaced by computers.
Yeah.
So we are replacing the most, the highest profession imaginable, right? There are others like medicine and so on, right? But, teaching, preparing young people for the future and so on, this is so important. And this is being replaced by computers. So we are replacing something that, now, suppose we have a nuclear plant and it has to be cleaned, right?
Mhm.
It's great that we can have robots that go there and clean the power plant, because if a human would go there, it would get radiation. This was done before robots in Germany. There was a book about that. I could describe it. Very interesting by a journalist. He forgot to be a Turk, and Turks were hired to go into power plants to clean the plants, but they got, I'm going to tell you the story, they got a passport, a radiation passport, right? And after some amount of radiation, they would be forbidden to go into the nuclear power plants. What did the Turks at that time, right, did? They lost the passport, right? And got another passport beginning with the radiation again. So they would get cancer, leukemia, and so on. And what happened in Germany, they would send back to Turkey. At that time, Turkey was not a part of the European Union and so on.
Right.
This was described by a journalist that for to be a Turkey to be to experience how these people were being treated in Germany, right? Now, if a robot could do that, great, why not? So I'm absolutely against replacing humans in two conditions. If the work degrades the human and there is no other work to be done. Right? If there is another work to be done, then it could be replaced. Even if degrades the human and there is no other work, maybe it's preferable that the human does that job instead of a machine. That's my position. Any other question?
There's no more questions. There's, well, it's kind of a question. Somebody's asking if they were to try to translate, and I put that in quotes, your talk about Turing machines and computers for primitive tribes in Africa, where would you start to try to explain what a computer is? If because where you began, they couldn't even begin into some of these tribes in Africa.
No. Well, I have a paper describing a Waldorf way of introducing computers. I developed a theater that I call a paper computer. What I do is I put the students right in front of the class, about, don't recall how many, 15 of them, and I assign each one a function. For instance, the storage units, storage words, right? Represented by each student. So each student gets a number, a storage number, right? Memory address, right? Another one is the central processing unit, the CPU, right? There is a pointer. A student has a how to say, plate, no, a shield, how to say, with the name pointer, right? And he is attached by a rope to the central processing unit. So where the central processing unit, I'm sorry. There is an arithmetic unit. A student represents this arithmetic unit, right? And where the central processing unit goes with the rope, he brings the central the arithmetic unit with him or her. And there is a pointer and so on. And then I load a program in words. So the tribe in Africa should have at least know how to read, at least that, right? And then I show how a computer works. I simulate, I load a program there. There are storage units with data and so on. And the program is then executed, and the program adds numbers until a negative number comes into the input. The input is also a person, and the output, the printer, is another person, and so on and so forth. And the CPU reads the input cards in the input and writes down in a piece of paper the output, and so on. So what I did is I introduced computers with this theater play, which is used by my colleagues at the university at the introductory courses in computer science, the first classes. And the students like very much because they do something, right? And it becomes real. Now, this is not a Turing machine. I think Turing machines are too abstract. That's why I give a lecture on Turing machines only for the last high school classes, not the primary school and so on. It is impossible. And probably the tribes in Africa would be in intellectual and cultural levels at the beginning classes in primary school. So how is it possible to show abstract concepts? You know, unfortunately, I've never thought about that, but I think it will be very difficult. Now, by my teacher play, if they know how to read, the only thing necessary for that theater play is knowing how to read. The instructions, the instructions are written in text. Add position 20, the contents of position 20 to the accumulator. There is a person is the accumulator, right? Add to what is in the accumulator and put the result into the accumulator. As the original computers work with one accumulator. Nowadays they have multiple registers that work with multiple accumulators. But anyhow, I think, and then afterwards, what I do is I code the instructions that were written as text. I write on the blackboard a code for them using four digits, right? 2 for the instruction code and 2 for the address. And I have a computer simulated. It's called hypocomputer from hypothetical, but it's with a HI because it's in Portuguese, hypothetical. Okay. And then I show how machine language works. And this is very, very important. If one doesn't understand how machine language works, it's not possible to understand how a computer works, right? And when I gave introductory courses into computer science, right, I used to introduce first the paper computer and the simulated hypercomputer and so on. And then I would go into a so-called high-level language. They are not at a high level, but that's another problem. A high-level language like nowadays would be, for instance, Python, right? I have a cheat sheet for Python on my website, but it's on in Portuguese, unfortunately. But anyhow, I would show every command of that language and translate it into that hyperlanguage for machine language, so that the students understand how a high-level command code is translated and interpreted by the computer. By the way, computers don't execute the instructions, they interpret the instructions. This .exe, yes, from the PC introduced by Bill Gates, is wrong. It should be int, INT, interpret. Because the instructions are interpreted, they are not executed. Anyhow, that's another problem. I'm sorry, I'm giving many lectures now.
Well, we'll call it a night for now. I want to invite everyone back for January 9th, when we'll be talking about AI and another way of interpreting AI. That'll kick off a new year just wonderfully for us. And I want to thank you. I know Valdemar was elsewhere, but because of weather and possible electrical outages, he actually came home to do this. And I really appreciate you doing that. So we didn't have any outages in the middle of this. So I hope you can get back to your cottage after this. And
it's 200 kilometers from here in the mountains.
Oh my goodness.
70 kilometers per hour is 70 kilometers is 50. 80 kilometers is 50 miles. So it's more than 100 miles. And we usually go there on a Sunday, so there is no traffic, mainly getting out of São Paulo, which is an enormous city, and with many traffic jams, and we return on Sunday. Yeah. But tomorrow is a holiday here in Brazil. It's the Republic Day, the day the Republic was declared, 15 November. And so we plan to come back tomorrow because it's a holiday. There would be very few traffic, but we decided to come today, and the difference is very little. It's not a sacrifice, really. And I came here because we live in a building, a condominium, and if there is electric outage, which happens here in São Paulo quite rarely, but in the mountains, it's very frequently. If there are too strong winds or too much rain, then the possibility that there is an electric outage is very, very, very common. So, but here it's not so common. If there would be an electric outage, we have a generator in the building, right? It's already there, prepared for this. Okay, and there is an outlet there on the corridor, and I just stick some cables and bring power to the modem router, which is activated by optical fiber, so it's not subjected to electrical outages. That's why we came here. But anyhow, it was not a big sacrifice at all. And I want to thank very, very much for the opportunity. As I think you have seen, I appreciate very much giving lectures, and appreciate the opportunity of speaking about things that many people don't know, and also going into philosophical considerations. And I hope that those that know anthroposophy have recognized the basis, the fundaments of my philosophical considerations. But I do it in such a way that any person can hear and understand. You understand? I'm transmitting anthroposophical concepts through a way that everybody can understand. I'm also using scientific concepts, mathematical concepts, and so on. And this gives, how could I say, this is a way of transmitting our concepts, in a way that people respect.
Yeah.
You understand? Because if I would, from the beginning, speak about the etheric body and astral body and so on, people say, "Wow, that looks interesting," but I like to think about other things. But if I present things this way, I presented today, nobody could say that I'm, in the technical sense, that I'm wrong. Right? They could say, "I don't agree with your philosophical conclusions," but the philosophical conclusions are understandable. That's very important.
It is. And for that, we all really appreciate what you've done and continue to do, even in your retirement.
And age. I'm 81.
Great. So, well, thank you so much. And we will see you in January on the 9th. So,
Great.
all
A
right.
big hug to everybody, right? A kiss to the
Bye-bye.
ladies. Sonia is
Bye.
also. Bye-bye. Ciao.